Problem session 8, question 7. Suppose that 15% of the families in a certain community have no children, 20% have one child, 35% have two children, and 30% have three. Suppose further that in each family, each child is equally likely to be a boy or a girl. Suppose a family is randomly chosen at random from this community. Let B the number of boys and G be the number of girls of this family. Part A. What is the joint probability mass function of B and G? To find the joint probability, we need to do two things. Let K be the number of total number of children. So K equals boys plus girls. The probability a family has exactly K children is given in the problem. So, given K children, each child is independently a boy with a probability 0.5. The probability of exactly B boys, hence it means girls is equals to K minus boy girls, is the binomial term, which is from K, we need to choose B, and since being a boy or a girl have 0.5 probability, we need to use this term. When we put all of these together, we will end up having this: boy number equals B and girl number equals G equals probability of number of children equals K multiplied by probability of being a boy or a girl. That's the joint PMF for boys and girls in a randomly chosen family. This one. Okay, so let's create a table. Let's write B, G in here, and number of girls in the first row 0, 1, 2, and 3, and boys in the first column. Let's make this straight. Okay, 0 boys, 1 boys, 2 boys, and 3 boys. So, as stated in the question, let's check it again. It says 50% of families in a certain community have no children. Okay, so this term is 0.15 in here. Let's fill this. 0.15 times, and then we need to write this part, actually this part. We have 0, that's why maximum we can get is 0, and then 0.5 to the power of 0. The next one, probability of having one child is 0.20, and from here we need to select 0 because this is girls and we are choosing boys. but it doesn't matter, it just relates how you design the function. And then we need to multiply with this term. Probability of having 2 children is 0.35, and we are going to choose none of them to be boys, 2 of them need to be girls. And actually we can write this like this too. Like at first, probability of having 0 boys multiplied by probability of having 2 girls. We can write this like this too, but let's just combine it like we write in here. And write it like this. Probability of having 3 children is 30%, and from 3 children we need to choose 0 for boys and then multiply the probability of having 3 girls. In the next row we are going to have 0 plus 1 boys, 0 plus 1 child in total, and that one must be a boy. So we are going to do the same thing. The probability will be the same with this one because we are having just one child. 0.20. From 1 we are going to choose 1 as a boy and then multiply it with this probability having 1 boy. In the upcoming part we are going to have 1 plus 1, 2 children. Probability of having 2 children is 0.25, as you can see in here. 0.25, 35, sorry. We are going to choose one of them as a boy and multiply with this probability. Actually, this is 1 for boy and 1 for girl. Same thing. In the upcoming part, we are going to have 3 children in total, and one of them is a boy. Probability of having 3 children is 30%. 0.3 multiplied by, we have 3 and one of them is a boy, and multiplied with this probability. The upcoming part will be 0 because we cannot have 4 children in total. That's why it's 0. In this part, we will have 2 children. That's why this is 0.35%. 2 of them will be boys. So this is the probability. In the upcoming one, we will have 3. The probability of having 3 is 30%. From this 3, 2 is a boy, and multiplied with this probability having 1 girl and 2 boys. And in the upcoming part we will have 4 children. This is impossible. In this part we have 5 children, this is impossible. In this section we have 3. Probability of having 3 children is 30%. Among these 3 of them is boy, and probability of having 3 of them as a boy is this. In the upcoming section we have 4 children, which is impossible, 5 impossible, and then 6 is impossible. Part B. What's the marginal PMF of B, boys? To find this, we need to write marginal PMF of boys. And actually let's write it over a table. Let's write number of boys in here and write the PMF in here like this. Summation of girls equals 0 to 3 minus boys. Probability of the joint one. When B is 0, we need to sum these values. Having 0 boys and 0 girls, having 0 in total is 15%, and we are not going to have any, so that's why this one is simple. Plus, this time we are going to have just 1 girl and 0 boys, as we stated in here. Having 1 child is 20% probability, 0, none of them is boy, and multiply the probability of having 1 girl plus with 35% probability you will have 2 children, none of them is boy, and probability of having 2 girls is this, plus now we have 3 children, 3 of them is girl, no boys, multiplied with probability of having 3 girls. For this part, when B is equal to 1, we are just going to have 1 child, and it's a boy, so this is this, and multiplied with having probability of having 1 boy, plus now we have 2 children, 1 of them is boy, now we have 3, probability of having 3 is 30%, and 1 of them is boy, multiplied with this probability. When B is equal to 2, now we have 2 children and none of them is girl, with 35% probability we can have 2 children in total, 2 of them is boy, and multiplied with having 2 boys, and we can have 3 in total. Probability of having 3 children is 30%, and 2 of them is boy, and you have to multiply it with having 1 girl and 2 boys. For 3, probability of having 3 children is 30%, 3 of them is boys, and probability of having 3 boys is this. So we just need to sum this part and write it like this: PB 0 is equals to summation of here, and do it for all of these: PB0, PB1, PB2, PB3. Part C. What's the marginal probability mass function of girls? Since having a probability of having a girl and boy is 0.5, we can say they should have identical distributions. So that's why we don't need to do everything we did in B all over again. We can just say the distribution is same with the one we found in B. You can just replace this B with G, these parts, and make manipulations in here and just write the same thing for part C. Part D. Calculate the expected number of boys in this randomly selected family, namely expectation of boys. To calculate the expected number of boys, we multiply each possible number of boys by its probability and sum over all possibilities. So from part B we have, let me write the probabilities first. Probability of having one boy is 0.3875. Two boys is 0.20, and three boys is 0.0375. So we write expectation of boys is equal to b equals 0 to 3 number of boys multiplied by having that many number of boys, which is 0 multiplied by 0.375 plus 1 multiplied by 0.3875 plus 2 boys, and its probability is 0.20 plus 3 boys, and its probability is 0.0375, and the answer is 0.9. Thus, on average, there are 0.9 boys in a randomly chosen family. Part E. Calculate the expected number of girls in this randomly selected family. Again, since they have identical distributions, the expected number of girls will be equal to the expected number of boys, and like we found in here, it's 0.9. Part F. Are B and G independent? Let's check it. To check if B and G are independent, we must have this. Equal to probability of boys and girls for every B and G pair. So let's pick this one. Probability of having 3 boys was 0.0375. Probability of having 1 girl is 0.3875. Their product will be equal to 0.0145. But in our table, let's check our table. We have 3 boys and 1 girls. We have 3 boys and 1 girls. It is 0 because it was impossible to have 4 child in total. So that's why a family with 3 boys can't have any girls, and that's why they are not independent.